Let's get started. Thanks everybody for coming to Astro Coffee. We haven't had one of those in a while. Remind people of them. It's my pleasure to introduce David Coria. He's visiting us from the University of Kansas, where he's working on his PhD with Ian Crossfield in his fourth year. David has a lot of different interests, including stellar abundances in particular, but also galactic archaeology and exoplanet science. David was actually part of the inaugural class of the NASA Exo Explorers program, which is a program by NASA to support professional development of graduate students working in the field of exoplanets. And I think actually Maria is current Exo Explorer. Is that correct? Okay, well, better ado, I'll hand it over to David. So David's visiting the whole week. He's been around the whole week, around for tomorrow as well, and just kind of agreed to give us a short talk on what he's been up to for his PhD. Please.
Yeah, so I guess first of all, thank you to all of you for having me. Having a great time in Hawaii so far, and I really do enjoy getting to see all the stuff that you guys are working on. It's all really cool. So like Dan said, I do work with Ian Crossfield and Ada Hijazi on stellar abundances. But today I'll be going over some recent developments in planetary abundances, specifically these new detections that we're seeing of carbon, nitrogen, and oxygen isotopologues in like the brown dwarfs and the Jupiter-class exoplanets. And then I'll go over my work briefly in trying to make complementary stellar measurements. So we'll see if this goes. It's been lagging a little bit.
Back to the long lag. Okay. I thought the internet in here is good, but maybe it was wrong. Around it.
Yesterday was fine, I think, when I was sharing. So
you were in the auditorium.
No, yeah, I was in here too. Yeah. Yeah.
Hey. We're gonna have to time your transition well.
So I guess for just a quick overview, I'm going to start with some background on these carbon, nitrogen, and oxygen abundances and why they're so important to understanding planet formation. Then we're going to go over, again, the most recent and like never before seen brown dwarf and exoplanet isotope measurements. And we'll finish it up with some of the progress that we've made in the KU ExoLab in measuring these carbon, nitrogen, oxygen isotopologues and cool dwarf exoplanet host stars to complement the new measurements. So in general, abundance ratios or the relative amounts of a certain element in a star or planet, they play a pretty important role in understanding protoplanetary disk structure, planet formation theories, and for exploring the shared history between between a planet and its host star. So carbon and oxygen abundances are particularly important for understanding planetary formation and the evolution of their atmospheres because of their influence on ice, gas, and rock chemistry. In gas-rich exoplanets, for example, the carbon-to-oxygen ratio acts as a sort of tracer of the planet's formation with respect to several snowlines, or the distance from a star where volatile molecules like water, methane, carbon monoxide, and carbon dioxide condense into ice grains. So ideally, the working theory is that depending on where in the stellar disk a planet forms or creates its envelope, we expect to see different atmospheric C/O ratios in the planet. And again, by measuring both stellar and planetary carbon and oxygen abundances, we can predict how far from the star the exoplanet formed. And then any inconsistencies in the actual versus the expected abundances are signs that the planet may have migrated to its current location. Of course, it's never quite that simple because we're seeing that the carbon to oxygen ratio alone isn't enough to constrain this type of formation migration, but also because studies of each component, so in this case, the stars, the protoplanetary disks, and the exoplanets, they each require observations from a different instrument. And of course, there's also different chemistries happening in each component. So it can get kind of tricky to actually sort out the link between the disks, the stellar abundances, and the planetary composition. But with the use of high-resolution spectrographs on large 8-meter class telescopes, we suddenly gain sensitivity to weaker isotopologue signatures that we wouldn't see otherwise. And these isotopic abundance ratios provide us with additional constraints for planet formation that we can potentially measure in both the host star and the companion planet. So the carbon-12 to carbon-13 ratio is one of these additional constraints. The theory is for planets that formed within the CO snowline, which is around 20 AU in solar type stars, we expect them to inherit their host star's carbon-12 to carbon-13 ratio. Beyond these snowlines, there are certain fractionation mechanisms that I won't go into too much detail, but they cause this like ice-gas partitioning between the major and the minor isotopologues, which leads to carbon-13 depleted gas and carbon-13 enriched ice. So this means that a planet that forms in the outer portions of the disk may exhibit a much lower carbon-12 to carbon-13 ratio than its host star because it likely accreted that carbon-13 rich ice. So just like the C to O ratio, this carbon isotope ratio could be another indicator for migration. And it's, again, particularly important because it has been measured in protoplanetary disks, host stars, exoplanet atmospheres, and even some brown dwarfs. Nitrogen exhibits a similar fractionation signatures that could be useful for tracing planet formation. So this is, again, a similar diagram. This time it's showing the behavior of the nitrogen 14 to nitrogen 15 ratio. So the disk is now split into an inner, middle, and outer portion by the ammonia snowline at about 5 AU around solar type stars, and the N2 snowline at around 20 AU. So here we can see that the inner disk shows a nitrogen isotope ratio that's consistent with its host star, but then the highest nitrogen, the highest nitrogen 15 enrichment is actually expected in the mid disk, and then kind of decreases as we go further out towards the outer disk. So this isotope ratio is pretty well studied in protoplanetary disks, but not so much in cool dwarf stars and exoplanet atmospheres. But naturally, I did say I was going to talk about CNO. So we would expect similar isotope fractionation signatures from oxygen. However, their stellar and substellar detections are pretty scarce in the literature because the minor isotopologue that's typically used is C18O. The signatures are just so weak in stars, brown dwarfs, and Jupiter-class exoplanets that's really hard to detect. But in our own solar system, we are able to measure the oxygen 16 to oxygen 18 ratio more directly using primitive meteorites that have fallen to Earth, like the Allende and the Murchison meteorites shown here. So what we see in these, that we see that their oxygen 16 to oxygen 18 ratios are pretty consistent with solar system abundances. And this, of course, means that the oxygen 16 to oxygen 18 ratio may not be as useful to planet formation tracing as the carbon and nitrogen ratios. So now I'm going to kind of switch gears a little bit and go over some exciting and relatively new isotopic abundance measurements that are made in super Jupiter class planets. And so again, the detections of minor isotopes like carbon-13 are exciting because they produce much weaker signals than their primary counterparts, which means that we can only detect these with high resolution spectrographs that are mounted on, the most powerful, largest telescopes in the world. So there are still very few isotope detections in exoplanets and their cool dwarf host stars, but those few, they definitely do stand as a testament to how sensitive these instruments actually are. So here is a relatively newly discovered planetary system called Tycho 8998. For short, that consists of a K-dwarf star and 2 super Jupiter-class planets. To date, Tycho 8998b is one of only a handful of exoplanets with this carbon-12 to carbon-13 ratio in the literature. But this system is particularly interesting because the B planet appears significantly enriched in carbon-13 relative to both the interstellar medium value, which is about 68, and the solar value, which is about 90. And this planet shows a value of about 31. Because Super Jupiter is located about 160 AU from its host star, which is far beyond the CO snowline and farther out than anything that we observe in our own solar system, it's likely that this carbon-13 enrichment is due to the accretion of carbon-13 rich ices. But without a host star measurement, it's really difficult to say whether this carbon-13 enrichment is actually due to ice accretion or if the entire system is enriched for whatever galactic chemical evolution reason. Unfortunately, there are no good stellar spectra out there that are suitable for CNO isotope analysis for this particular star. And as we go through this kind of the rest of this talk, you'll kind of see that this is a problem that I've been running into very frequently. So in addition to Tycho 8998, there have been more and more carbon-13 detections showing up in the literature. So here I show just 3 different systems, and I've highlighted a couple differences. So you'll see WASP-77AB and HD 189733b are both hot Jupiter-class planets that orbit very, very close to their stars, which is well within Mercury's orbit in our own solar system. But these planets were observed from the ground-based 8-meter class telescopes in near-infrared spectrographs. And then in the middle, we have VHS 1256b, which is a really bright and young wide-orbit super Jupiter that was observed with the near-spec instrument on the James Webb Space Telescope. Another pretty interesting thing to note is that the error bars on the James Webb measurement are very, very small. So it's looking like James Webb is going to be able to be really, really good at doing this. But besides that, you'll also notice that each of these planets shows a carbon-12 to carbon-13 ratio that's around or below the interstellar median value of about 68. But unfortunately, again, there aren't any complementary host star measurements for comparison, except now for WASP-77A, which is what I've been working on lately. Again, regardless, it's interesting that these are all subsolar and that we see similar values for planets really close to and really far away from their host stars. Don't quite know what it all means yet, but hopefully we'll get there. So yeah, now moving on to nitrogen isotope measurements, there's hardly anything in the literature in dwarf stars, brown dwarfs, and exoplanets. But very recently, just last year, actually, there was a minor isotopologue of ammonia detected by the MIRI spectrograph on the James Webb telescope in this rogue brown dwarf that's named WISE-J 1828. So on the left, you can see just a couple of lines that they use in their analysis. But this result is pretty cool for a couple reasons. So first of all, the ammonia features that they use are located at around 9 to 11 microns. So typically, ground-based observatories don't provide much coverage past the 5 microns. But we know JWST's MIRI instrument was built to do just that. Second reason is that WISE-J 1828 is a wide dwarf with a temperature of around 380 Kelvin. What we know is that ammonia dissociates at much hotter temperatures, and so it's expected that we'll only be able to see these sort of isotopologue signatures in the atmospheres of the coolest wide separation planets or in the coolest brown dwarfs in this case. But besides this detection, the nitrogen 14, nitrogen 15 ratio has also been derived in pre-stellar cores, in some solar system planets, comets, and meteors. But again, there's still no measurements in cool dwarf stars or Jupiter-class exoplanets of this nitrogen isotopologue so far. So for oxygen, these aren't quite as scarce as the nitrogen isotopologues, just because they're measured alongside the carbon isotope ratios using just the minor isotopologue, the weaker one. So in brown dwarfs and Jupiter-class exoplanets, we're also starting to see just like hints of the oxygen 18 signature. So we have Yaping Zhang, who reports a tentative oxygen isotope ratio that's about 3 times the solar value in this brown dwarf called 2MO355. And this is kind of more comparable to values that are reported in studies of young stellar objects and M-dwarf binaries. The problem with this particular one is that it's very poorly constrained because they have really, really low signal to noise data, so about 2. In VHS 1256b, we see a new and honestly pretty astounding constraint of the oxygen 16, oxygen 18 ratio using retrievals of this mid-infrared band of some James Webb near-spec data. They find oxygen isotope ratio that's equal to 425. But the cool thing is that they also detect oxygen 17, which hasn't really been measured before in either dwarf stars or exoplanets, just because, again, this oxygen 17 signature is even weaker than the oxygen 18 signature. Again, all of these ratios are lower than the local interstellar medium and the solar system values, which suggests that the abundances of the more minor isotopes are enhanced compared to the primary. And of course, this can be driven by different isotope fractionation mechanisms that, again, I won't get too much into. In terms of stellar measurements, the best avenue for measuring oxygen isotope ratios in cool dwarf stars is likely in the near infrared H and K bands, where we see absorption from carbon monoxide that's typically used to derive these isotope ratios. But also something new is that we're able to see these signatures from water isotopologues too. The problem again is that in hotter stars, water dissociates and we can no longer use these to derive elemental or isotopic abundances. And there are also far fewer of these near-infrared spectra available than the optical. But we do unfortunately need this near-infrared wavelength coverage because there are no good oxygen-bearing molecules with absorption bands at visible wavelengths that could be used to derive the oxygen isotope ratio in stars. Yeah, so hopefully by now you're kind of understanding that we're seeing more and more of these cool isotopologue detections in brown dwarfs, giant exoplanets, but not very many complementary host star measurements. So this is kind of where my work comes in. Despite these cooler K and M dwarf stars being notoriously difficult to model because of just this overwhelming molecular absorption and blending, we have actually been able to fit these spectra and measure elemental abundances pretty well in the near infrared. So here I show some selected lines for the abundance analyses of a couple cool dwarf host stars. So we have Kepler 186 and 138 on the top by Diogo Suoto, who's one of our collaborators. And on the bottom, we have WASP 107, which is the paper led by our postdoc, Neda Hijazi. So just kind of like glancing at that, you can kind of see that the best fit between the model spectra and the renormalized observed spectra just sort of like demonstrates our ability to accurately model the spectra of these cool dwarf stars in the near infrared. And then, of course, from there, we can go on to derive their elemental abundances. Recently, this is just kind of a plug, our postdoc Neda has developed and submitted her spectral fitting and abundance calculation code called AutoSpecFit, which allows us to sort of automate this process that turns to be more complicated than I originally thought. She's kind of been teaching me how to do all this stuff. But basically the way this works is that after we go through a careful line selection process, the pipeline begins by generating synthetic spectra for each element using the physical parameters of the star. So effective temperature, metallicity, surface gravity, and microturbulence. But we do that with varying relative abundances of a particular element ranging from about negative 0.3 to positive 0.3 dex and steps of 0.01 dex with solar abundances for all the other elements. But once we have this grid of models for the first iteration, we calculate individual abundances using a chi-square minimization routine. And then for the next iteration, we create a similar set of models for each element, but this time we use the abundances from the first iteration for the rest of the elements. So the code then repeats the model synthesis and the chi-squared minimization until all the abundances converge to their final values. So this approach differs from traditional abundance calculations in that traditional grid sampling would require an extremely large number of models to be already in hand. But with this iterative approach, we reduce that to about 610 models generated per iteration. Still a lot, but not as big as it could be. But also this approach allows us to take into account how the changes in when elemental abundances affect the spectra and also how they affect the value that we calculate for the other abundances. And here's just a plot that's showing kind of how the abundance values change with each iteration. The final abundances that we're seeing, I guess I never mentioned we're kind of practicing the code with KU 18. So if any of you are interested in that particular system, we'll be publishing the results on that soon. But the final abundance values for each element, they have uncertainties ranging from about 0.03 to 0.26 dex. And really, it kind of depends on how sensitive each species is to the physical parameters of the star. So if we have really small uncertainties on the effective temperature, surface gravity, metallicity, we get pretty good constraints on the elemental abundances. But with this new code, we can kind of avoid some of the issues that I've been running into while deriving the carbon 12 to carbon 13 ratio in this host star WASP 77A. So I found that model spectra generated using literature values with parameters of the star with solar abundances don't quite reproduce the observed spectra like in the CH line that you can see there. So if we can't fit these stronger lines of questions, then how the heck are we going to measure the isotopologues? So I guess what we're seeing is that we may have to first determine elemental abundances before the isotopic ratios, especially when we're dealing with the weaker lines at optical wavelengths. You can see here that for this particular 13CH line, where the model set was generated using solar abundances, we measure solar carbon-12 to carbon-13 ratio. And of course, this shows a significant difference between the host star and the companion, which seems enriched in carbon-13. However, if we perform kind of like a rough elemental abundance fit first, we get a better fit overall between the observed spectrum and the set of model spectra. So in this example, I just sort of varied the stellar metallicity and the elemental carbon ratio in steps of 0.1 dex and found that negative 0.2 dex was the closest fit by eye. So now we see actually more of a subsolar carbon-12 to carbon-13 ratio, right around 55 in the host star, which is much closer to that that's estimated in the companion, which of course completely changes the original interpretation. So overall, what this means is that we can add more chemical abundance constraints to better understand the planet's formation and accretion history. So here I've kind of compiled a table of all the different stellar abundances on top and planetary abundances on the bottom. But we also see that my new isotope ratio in the star is pretty consistent, I want to say, with the hot Jupiter's carbon-12 to carbon-13 ratio. So again, we still kind of have to do some more work to figure out what it all means. But the gist is that with more and more stellar brown dwarf and exoplanet CNO isotopologue ratios, we can start to discuss the differences between stars and their companions, between brown dwarfs and super Jupiters, and between hot Jupiters and wide orbit Jupiters, and really start to piece together the planet formation puzzle. So yeah, in the era of James Webb and the ELTs, we can characterize exoplanet atmospheres like never before, but it's really important to contextualize them properly. And this means, of course, characterizing the host star as well. For the rest of my time at KU, I'm going to continue trying to identify more of these formation tracer abundances. I think I'm leaning more towards nitrogen and sulfur is what I'm seeing might be pretty useful. And then trying to measure them as best I can in the stars hosting these Jupiter-class exoplanets, where most of the measurements are being made. But in the meantime, keep an eye out for my paper on the carbon-12 to carbon-13 ratio in WAF77A, and we'll see what the system's abundances may or may not tell us about the planet's formation. Oh, thank you.
Well, thanks, David. I fully endorse your key takeaway. Embrace the whole star.
No.
Questions today?
So like one thing just at the end here with like WASP-77 and you can find that that has a higher abundance of C12 and C15 than its planet, right? Is it feasible to like at least back of the envelope say like, oh, what if another companion planet in the system go for the star at some point? Is that enough to affect the ratio in that much? I don't know if that's
kind of like an engulfing scenario,
something like that. Like, is that feasible? Can you pull that kind of? Can you like kind of backtrack that information out in just like very broad terms, like not?
Yeah, no, I guess it'd be hard to say. I don't know that I've seen very much modeling as to how. I'm sure the elemental abundances, of course, would produce some sort of difference. Mostly like the refractory abundances. Yeah. Again, it's something that you work on. I'm not too sure with these volatile abundances, kind of what the chemistry is there. And again, these isotopologue signatures are so weak and the abundances are so low, it's kind of hard to say definitively where we'd be able to kind of trace that out.
Right, yeah, no, that's fair, yeah.
So in systems where you have a giant planet that you're able to get a spectrum of, would that say anything with the formation, if you're able to pin down sort of some of the planet formation from that, would that say anything about other planets in the system? Like, because I know one of the systems that you showed has a rocky planet in it as well, Kepler 138. And so I was wondering if there's any jumps or correlations you can make to the other planets in the system that aren't the ice-rich or gas-rich planets? Or...
So I guess like the main thing that we'd be able to just kind of see in terms of planet formation is we expect sort of different isotope enrichment, whether a planet forms like a star, so like top down, or like accretion bottom up. So of course, when something like gravitational instability, something collapses, you expect to see signatures that are more consistent with like solar values, whatever abundance that may be. But then once you form from the bottom up, you start to see different signatures. So you see more enrichment of the minor isotopologue, or that's kind of like what's expected, just because at different regions of the protoplanetary disks, we see more and more of the minor isotopologues become like trapped in like ice and dust grains and that sort of stuff.
Yeah. And then you could maybe assume that most of the planets in the system formed a similar.
Yeah, I think so.
Wonder how well do we know about intrinsic variance of the ISM as well as muscles? Alex.
That's a good question. I don't know if I have a good answer for you. I mean, something that we see in our own solar system with the oxygen isotope ratios, especially, is that we observe different like pockets that have just like slightly different isotope ratios, because the kind of protoplanetary disk at that where all these meteorites and stuff form, it's not homogeneous. So we do see just like slightly different variations among that. So what we're really looking for, I think, is just like really significantly different ratios between those stars.
I think I recall, maybe you can correct me if I'm wrong, but people have studied solar twins in the solar neighborhood really precisely found that the ratios are pretty similar between all of them. So that would suggest that there's not a like Megan Bedell. Yes. Any questions online? We got folks online. All right, I have one last question. So one of the striking, I guess, takeaways is that we're sort of lacking the stellar information, but we have it for the planets in many cases. Which most cases it's always the other way around. Like we know a lot about the star, but it's hard to learn something about the planet. So these advances now are measuring these isotopologues really well. How much does that vary in terms of spectral type? Surely, if you go like mid and late M dwarf, it becomes harder, I presume. I forget what the spectral type was.
Yeah. WAS77 is a K. Okay.
So if you would want to, know this about TRAPPIST-1, for example, how hard would TRAPPIST-1 be compared to?
I guess that's kind of like the next step to see how well we can actually do this. But we're pretty hopeful that we'll be able to derive these isotope ratios in the near infrared with the H and K band spectra. I think we have a spectrum of TRAPPIST-1, but I haven't taken a look at it. Okay. But yeah, like there's just a lot of CO absorption in the K band that could be used to derive the ratio. We just don't know quite how precisely it'll be yet, or there's a lot of blending that goes on too. So we're not sure how well we'll be able to parse it out. But
how cool do the models go?
Let's say maybe like 27.
Right, so that's a little bit. Okay, I think we're at the